Good morning, everybody. My name is Ashutosh Garg. I welcome you all to our third session on fired heater design. I work for Furnace Improvements. Our company is in the business of improving performance of fired heaters. We completed 25 years in business last year, so we decided to do this training about what goes on in designing a fired heater. I know most of you are end users or in engineering companies and may have had some exposure to fired heaters, maybe design. But this webinar, which is a 12-part series, we want to talk about what goes on in designing fired heaters, the step-by-step, so that you can understand the importance of a number of parameters. And if you are working on fired heaters or if you are buying fired heaters, hopefully this series will help you. And today we will be covering the most important section of fired heaters, radiant sections. We have devoted 2 sessions. The next session also will be on radiant sections because radiant section is huge. We are trying to cover it in 2 hours. Let us see if we succeed or not. So with that introduction, hold on just a Okay. I think let me see if I can get rid of side panel, hide side panel. Right. Okay. As I said, my name is Ashutosh Garg. I am the founder of Furnace Improvements. I have been working in fired heaters for almost 2/3 of my life. I'm a chemical engineer from IIT Kanpur. Currently, I'm working as a solution provider at Furnace Improvements, providing value-added solutions to our clients. The presentation today has been prepared by my team in Noida, India, and I want to thank them for preparing all the slides and all the materials. I'm just the presenter today. Let me talk a little bit about Furnace Improvements. It's a very different type of heater company. It's not a usual heater company which design, engineer, supplies fired heaters. We took on this challenge of working on existing fired heaters because no heater company wants to get their hands dirty. Fixing old fire heaters is a very dirty business, and we thought, let's take up this challenge. And that's what we have been doing for last 25 years. We have 2 offices. We have a main office in Noida, India now, that's what I call it. And we have an office in Sugar Land, Texas, which is basically our project office, project engineering office. As I said, our main business is improving performance of existing fired heaters. And we work directly with end users and owners. We have a doctor's-patient relationship. And one thing which is very unique with us is we have a contrarian approach. We always challenge the conventional wisdom. And a lot of times we have been very successful, and that's why we have 3 patents today for improving the performance of fired heaters. We also take pride in doing high quality technical work. Because of 2 offices, we are always working around the clock. We can keep schedules. We are supplying heaters currently to a client in about 6 months' time. And we have a policy of do it once, do it right. That's what we do it all the time. So we are a full supply company. We have a process group, we have mechanical and structural group, CFD modeling is also there, and 3D modeling. We produce our own fabrication drawings. So basically we can do design, engineering, supply, and even erection of fired heaters. That's what we have been doing. We have been revamping projects, and we have been guaranteeing the performance of your existing fired heaters. That's how confident we are of our performance. Uh, I want to take this opportunity to thank all our clients in US. Most of the work what we do, 90% of the work we do is in US based, although the center of refining is shifting, and we are doing some more work these days in India and other places. But once again, thanks to all the clients and for their trust for the last 25 years that we have been in business. So this is the third webinar, and fired heaters, I don't want to scare you, but they are almost very complicated. So what I mean by complicated is that the first webinar which we did, we spent about 1 hour talking about what information is needed for designing fired heaters. What type of information do you need to provide for design of fired heaters? What fluid you are heating, what are their properties, what is the plot area, what are the environmental considerations, fuel and sulfur content, efficiency content. So there are so many things you need to get it together before we even start designing. So we spent about an hour talking about the major design parameters in our first webinar. Then in the second webinar, we talked about combustion. Combustion is unique to fired heaters. It's the only equipment in the refinery where you can open the PEEP doors and you will be exposed to flames. So we talked about combustion, excess air requirements, fuels. Nowadays, we are lucky to have only fuel gas, but previously we used to have fuel oil. Acid dew point, we talked about a little bit about hydrogen firing, what is going to be the future, what are the factors affecting thermal efficiency, and these type of things. So that's what we talked about in our second webinar. Those of you who missed our first and second webinars, we have these recordings available on YouTube and even on GoToWebinar site, so you can always watch the previous webinars. This. So what we decided to do was to take a real life problem. This is a hot oil heater which we designed for a client in Louisiana about 7 years ago. And this has a very unique design. So that's why I'm presenting it to you over here. I have changed a few parameters to even make it more interesting. But this is a hot oil heater, 126 million BTUs, heating terminal 66 from 480 to 600 degrees. Pressure drop available is about 40 psi. The client wanted 90% efficiency. So the moment you talk about 90% efficiency, you have to give air preheater, especially if they don't want any waste steam. So that's what they wanted. So today we'll be talking about how we sized the radiant section for this hot oil heater. The fuel which we are using for this exercise is not a normal fuel. I just wanted to demonstrate the effect of different components in fuel. So I came up with this composition, which is 25% methane, 25% ethane, 25% ethylene. Ethylene is unusual. And then I put 25% hydrogen. So basically you can see even though the hydrogen is 25% by volume, by weight, it is only 3%. So you can see hydrogen is a very unusual fuel, and we will see, you've already started seeing as people are talking about hydrogen that a lot of unique things will be happening, So same thing what I've done over here is selected a site El Paso, and the reason I selected El Paso is about 3,500 feet elevation. And the reason, one of the things which affect the fired heater design is the site elevation and also the maximum ambient temperature. So these are the two parameters which uh, control the stack design. And also they affect the burners, they affect the pressure drop. The air is lighter when on higher altitude. So it makes a lot of difference, in the design. You cannot take a heater which is designed for at sea level and then put it at a hill station. We cannot do that. So uh, that's why I selected this. Another reason I selected this was the client wanted 10 ppm NOx and ammonia less than 10 ppm. NOx is oxides of nitrogen, and they are not good for humans. So we want to limit NOx formation. There are two ways we can do ultra low NOx burners, and post combustion is SCR. But for getting 10 ppm NOx, the only way is to put an SCR. So we installed an SCR, and that is another reason I selected this problem, is to show how we installed the SCR. We will cover it later, but I'm just giving you all our design limits. So when we did heat balance in our last webinar, the client wanted an efficiency of about 90%. The inlet fluid temperature is 480. We had different choices of flue gas temperature approach. Flue gas temperature approach means the flue gas leaving the process coils in convection. And we deliberately selected 200 degrees to get a temperature of 680, because at 680 the SCR catalyst has the highest efficiency. At lower temperatures, the efficiency goes down. So we selected a 680 degree temperature for the SCR. And then we installed an air preheater because the client wanted 90% efficiency. So we installed an air preheater and cooled the flue gases to about 365. And as a result, the air temperature goes up from 60 to 435. And we have an air preheater of about 11.3 million BTUs. And the calculated thermal efficiency is about 90.2%. So we did this heat balance last time, simple heat balance. Heat loss we assumed is 2.5% based on API 560. Those of you who don't know what API 560 is, API stands for American Petroleum Institute, and they have the standard 560 for fired heaters for the last more than 30 years. And it's almost like a Bible for fired heaters. Makes a good reading. So here my colleagues have done this combustion products. What will be the firing rate for this heater? We calculated 138.3 million BTUs. Then we calculated what will be the fuel gas flow rate, about 6,455 pounds an hour. We came up with combustion air flow rate, total flue gas flow rate. So we did all these stoichiometric calculations so that we can make the enthalpy curve for the flue gases, and then we can do the heat balance. So this is a very standard exercise we do. So we start with the combustion as one of the first steps for doing fired heaters design. So today we will be sizing the radiant section of this fired heater. We'll talk a little bit about radiant heat transfer, different configurations, single fired, double fired. Then we'll talk about the most important parameter in any fired heater, and that is the average radiant heat flux. We'll talk about vertical cylindrical and box heaters, tube size and number of passes, firebox geometry, burner layout, convection layout. So I think if we can cover these things in the next 40-45 minutes, then we will cover the design example, the actual design calculations in the next webinar. Let us see how far we are able to go, because everything takes time to explain, It's a very important. And those of you who are interested in learning more about radiant heat transfer or how a fired heater is designed, my colleagues have listed some of the references. As you know, Walter Lobo and James Evans, they wrote this paper in 1942, which is even used today, even after 80 years, by all companies. Any fired heater company you go to, they will still be using same correlations, including the FRNC and heater same. So everybody uses the same correlations and makes some minor adjustments. There is a very good paper on fired heaters published by R. and Wim Press, I think back in 1960s. It was published in Hydrocarbon Processing. You can refer that. That also gives you a very simplified method for designing fired heaters. So you can do that. There is a chapter in DQ process heat transfer. That is also very, very useful if you want to go through that, at least the radiant section. And then, as I said, fired heaters for general refinery service. API 560 does not tell you how to design fired heaters. That's one thing. It is more about specifications of fired heaters. How you specify fired heaters, what are the important things you need to specify. That's why we have listed over here. So this is kind of a design references what we have given for you. If you are more than welcome to refer all of them. So today we are talking about the most important component in the fired heater. We are talking about radiant section, where the heat is transferred to the tubes by radiation, predominantly radiation. Typical radiant section absorbs anywhere between 60 to 80% of the total heat duty. This depends on number of factors, and if you are thinking of steam reformers or ethylene crackers, there this number goes down to as low as 40-45%. Radiant tubes are generally spaced at 2 diameter pitch, and they are placed at about 1.5 NPS spacing from the refractory. And the reason for this is what we are processing is hydrocarbon fluids, and to get better heat transfer, we want the back of the tube or the backside fluid to be heated as well. So that is why we place these tubes away from the refractory so that we can get good heat transfer in the back. And we will, if you read a few literature, what we have, this thing, you will understand it very clearly. Very, very basics. I think all of you know, I don't need to put it, but I still thought I will add it. Radiant heat transfer is heat transfer by electromagnetic waves. Radiation always travels in straight line, does not require any medium or any contact. And radiant heat transfer is governed by Stephen-Boltzmann equation, where Q is proportional to T raised to the power 4 of the hot and T raised to the power 4 of the cold. Here, hot will be the flue gases and cold will be the tubes. And we are talking of absolute temperatures in degree Rankine or degree K. That is generally how the relation is described. So radiant heat transfer is very, very important. And let us talk about how the radiation heat transfer takes place in a fired heater. So we have direct radiation. Most of the radiation is the direct radiation from the hot gases to the tubes. We do have, as I said, re-radiation from the refractory walls to the tubes, whatever is going from the gap, and that hits the back of the tube. So that is a re-radiation, And then we have convection from hot gases to the tubes. Approximately about 15% of the total heat transfer in radiant section happens by convection. 85% by radiation, 15% by convection, and that is how the total heat is received. Now, but this heat is received on the outside of the tube. And then we have conduction. We have conduction mode of heat transfer, which is transferring that heat from the outside of the tube to the inside of the tube. And once the tube is heat is transferred to the inside of the tube, now it has to be transferred to the fluid. And fluid gets heated by convection actually. So if you see, even though we are talking of radiation, the conduction and convection play an important role in fired heaters. If the tube is fouled externally or internally, we won't have good heat transfer. If the fluid velocity is low, again, we won't have good heat transfer. So convection, conduction, and radiation, they are all in equilibrium and they all need to be dealt properly and done. When we are designing fire boxes or radiant sections, what are we looking at? We are looking at uniform heat distribution. Although in real life, it does not happen. I have not seen a heater where the heat transfer is uniform from top to bottom, but that's what we are aiming for. We are also aiming for good H by D ratio or good H by W ratio. We are looking for good combustion, draft and excess air control, and no flame impingement. We are also making sure that everything gets all flames, all combustion takes place in the radiant section. We don't want any combustion taking place in the convection section. So these are some of the design considerations which go into fired heaters. Now let's talk about how we design radiant sections. So two things. One is all the correlations are empirical. I mean, what it means is it happened first and then they came out with the correlation, And the fired heater design has evolved over the last, I would say, 120 years. I mean, if you look at the old fired heaters, everything used to be there was no radiant section. It always used to be all convection section. And when those heaters started burning out, there was a thought, and that's, I think, around 1940s, they started building a radiant section. So initially it was all convection section. So it's all empirical, and radiant section calculations are iterative actually, that we make certain assumptions and then we check those assumptions. So there are two things which are happening major. One is the radiant heat transfer is taking place, which is based on the flue gas temperature or absolute temperature of flue gas. And second is the heat balance, because once the heat is being absorbed in the radiant section, the flue gas temperature cools down. So what we have to do is to achieve a balance between the two, We want to make sure that the radiant heat transfer and the energy balance is achieved, And we do this, we repeat this process till we get a balance. Now, the funny thing is, when I started my career, there were no calculators, there were no computers, and we would do everything by hand. And it would take 3, 4, 5 days just to even run one set of calculations for a radiant section. Then came computer calculators and things became easier, and then came computers. And now the situation is my engineers can design some of these things in less than an hour because computer speed is so fast that this iteration kind of has become meaningless. They run thing and then they run another. So within 5 minutes, they have converged on the solution. Now the downside is they don't get a feel of the parameters. They just run the simulation and they get the results, but they don't get the feel. So I mean, there is both upside and downside. But radiant heat transfer is iterative. We think that let us design a radiant section, let us do all this calculations of surface and coils and burners, and once that is done, then we will do the heat transfer calculations and see whether we can get a balance, if we are achieving. If we are not getting a balance, we will make adjustments to our radiant section, then again do it. So this iterative process continues till we get a balance. So in radiant section, we can have two types of coils or two types of firing. One type of firing is most common, which is burners in the center, tubes on the wall. And that is called single firing, single fired. And the second one is burners are near the walls and tubes are in the center. And the tubes are getting heated from both the sides. Now there is some advantage when you heat the tubes from both the sides. And that is we can use higher radiant flux, we have lower surface area, lower fluid side pressure drop, lower residence time, and uniform heating of fluid. I mean, if you're thinking about steam methane reformers, ethylene crackers, modern coker heaters, modern hydrocracker heaters, I think they are all generally double fired. The disadvantage of double firing is we have a large firebox, lots of burners, and higher cost. So for most applications, I would say 95% of the applications are the first one, single fired, what we generally you will see in most of your heaters, tubes on the wall and burners in the center. That's some configuration which is mostly possible. This is just to give you some idea. The heat transfer across the furnace, across the tube is not uniform. It is the highest at the place where the flames are seeing the tubes at the front of the tube and lowest at the back. So this circumferential factor defines the average to max ratio. And generally for the normal 2D pitch tubes, the circumferential ratio is 1.8. That means the maximum flux is 1.8 times the average flux. If we increase the spacing to 3D, it goes down to 1.5. And if we do double firing from both sides, then it goes down to 1.2. So you can see we can do double firing and get down to the maximum. Now, what is the significance of maximum flux? Maximum flux defines the maximum film temperature, maximum tube metal temperature, defines the metallurgy, so it defines a number, it basically controls a number of parameters. So it does have some significance, maximum flux normally will, when we're designing it, the users will specify or the licensors will specify that I don't want the flux to be more than 1.8 or 1.5, Let's talk about the most important parameter what we use in fired heaters, and that is the radiant heat flux. Radiant heat flux is radiant heat duty divided by the surface area. So radiant heat transfer per square foot of tube surface. And why do we need to define this or control the flux? Because we are processing hydrocarbons, and hydrocarbons are very sensitive. So as the film temperature goes up, the coking rate goes up. And when the coking rate goes up, the run length of the heater goes down. So we want to make sure that your heater runs for a certain amount of time. It could be 2 years, it could be 4 years, it could be 8 years. I don't know. I mean, but basically, everybody wants their heaters to run forever. So as a guideline, lower heat flux is better for your heater. But you also need to watch out that lower heat flux means bigger heater, more money. So there is always a balance between the two, you know. So this is a average guide for heat fluxes and mass velocity, you know. And I have a thumb rule. If you don't know the flux you want to go with, just use a number which is very, very safe, is 10,000. I mean, most of the time, if you go with 10,000 flux, you won't go wrong, you know. I mean, if you have a special heater, then it's different, but 10,000 flux is a pretty decent number for most of the refinery services. Other thing you want to specify is the mass velocity, and we have some guidelines over here. I do want to talk about another equipment, because most of the technology in fired heaters has come from boilers. Now in boilers, we are heating water, and water is an excellent conductor of heat. So we are not worried about coking or film temperature. And there, sometimes we use fluxes as high as 45,000 BTU per hour foot square, actually. That's how fluxes go up in boilers. So 100 million BTU boiler may be 1/3 the size of 100 million BTU heater, you know. So very, very different approach. So another thing which we want to control for uniform heat transfer is H by D in vertical cylindrical heater, or H by W in box heaters or cabin heaters. API 560 gives maximum H by D of 3 for VC heaters, and they have now gone up to 4. Both numbers used to be 2.75. My recommendation is don't exceed 2.5 or 2.2. I mean, the lower the better. I mean, the lower this thing is, lower you will have maldistribution of heat flux, because the heat flux at the bottom and at the top is going to be very different. In fact, it's going to be highest at about 1/3 the height. So there are a lot of factors which come into this thing, but try to stay away from very tall, narrow heaters, you know. So let's talk about a very common design for refinery heaters, and that is a horizontal tube box heaters. Very good design, and generally the tubes are on the side. We can put tubes in the roof, and we have a long convection section. We have burners in the center. Good design, actually. We use it very often, and you will see mostly crude heaters, vacuum heaters will be in this configuration, you know. And historically, the tubes have always been horizontal in the old designs of heaters, and in the new designs, we have the vertical configuration. So here is a configuration of vertical cylindrical heater, a very, very popular design. It's a space-saving design and cost-saving design, you know. And then in vertical cylindrical heater, you are going up and up. So there is, the space is consumed is very, very little. We use only few burners. The convection section is very compact. So that overall cost of a VC heater is 10 to 15% lower than a cabin heater, you know. And the reason we are talking about this is that in our project, what we are talking about, we had a very tight requirement of the space. So the client said, I have to put this heater in an existing unit, and we only have 80 feet by 50 feet. That's all we have. And I still want my air preheater. I still want a fuel gas skid in this place. I want ammonia injection grid skid, ammonia injection skid for the SCR also in this place. So that's all I have. And if you can fit a heater, we want to see how will you design. So I will show you what we designed, later actually, but we came up with a unique design of air preheating system, and that's how we saved the space. But anyway, let's talk about what can we fit over here in terms of whether we can fit a box heater or whether we can fit a vertical cylindrical heater. So one thing about box heaters is when you put horizontal tubes, whatever tube length you have, you need an equivalent amount of space, empty space, for removing or pulling those space tubes. So that's called a tube removal space actually. So that is becomes you require a lot of space for box heaters. So here we started, the first thing we said, okay, what is the rate difference, split between the radiant and convection? And generally, as I said, 60 to 70% is absorbed in the radiant section and remaining 30 to 40% in the convection. So we are assuming a split of 66%. This is come up from the computer, even though we may start at 60 and then go to 66, or start at 70 and go down to 66. So depending on whichever way we go. So it shows you 66% heat duty. So radiant heat duty is 0.66 into 126 is about 83.2 million BTUs. That's what our radiant heat duty is. And then we selected a heat flux of 10,000. So once we select a heat flux, we know how much surface we have to provide. We take the radiant heat duty divided by 10,000 is 8,320 foot square. Very simple calculation. We are not doing hi-fi calculations as yet. We are just doing simple arithmetic calculations. So we need to provide about 8,400 square foot of heat transfer area for this radiant section. Let us see how we can provide that surface. So as I said, when we talk about radiant section, and radiant section is the most important section, we also have to select the tube size and the number of passes. And I have an option to select a 6-inch pipe, a 5-inch pipe, and a 4-inch pipe. What is the difference? If I select a 6-inch pipe, I will have fewer number of passes, and operationally, owners prefer fewer number of passes because then they have to do less pass balancing. If you have a 4-pass heater and if you have an 8-pass heater, you will see 8-pass heater is really difficult to control as compared to 4-pass heater or a 2-pass heater. So larger tubes give you more reliable operation. But at the same time, as the tubes become larger, they become thicker. So as they become thicker, they need more metal for the same surface area, so they become more expensive. So a heater vendor, and I'm a heater vendor also too, so don't get me wrong actually. We always start with a 4-inch pipe. We will try to give you a 4-inch pipe because 4-inch pipe is the cheapest in the industry. So we always, when we are designing it, our first instinct is to use 4-inch pipe. So we had an option of 6-inch pipe, 5-inch pipe, and a 4-inch pipe. 3 pipes size we selected, and let us see how they come up with. So our option is how many passes will be there, and how can we collect the total tube length. Total tube length is very simple. We have the total surface area divided by the surface area per foot, and that will give us how much pipe we need. So I have selected 3 pipe sizes, 4-inch, 5-inch, and 6-inch. These are the ODs. This is how much surface they have per foot, linear foot, 1.178, 1.456, 1.734. So if I'm going to be providing 4-inch pipe, I will be providing 14,000 total tube length. A 5-inch pipe will be 11,000. 6-inch pipe is 9,589. And this is a very familiar pressure drop equation for calculating pressure drop. F is the friction factor, G is the mass velocity, ST is the specific gravity, D is the diameter, So it's very simple equation. We calculate the pressure drop and we come up with this thing. So I take the total mass flow rate, 1.8 million pounds an hour, and I select 4-inch tubes. I come up with 4 passes. My mass velocity is very high, 1400. I go to 6 passes. My mass velocity is still very high. If I go to 8 passes, my mass velocity will still be very high, 700. So I may end up with 12 passes to handle 1.8 million pounds an hour. So we decided 4-inch pipe is not the way to go forward. Then we went to 5-inch pipe. Again, with 4-inch pipe, the mass velocity is 900. 6-inch is about 600. I may have to go to 8 pass, and even 8 pass will be, 400 or something. So we said, okay, let's go back. So then we went to 6-inch pipe, and we looked at with 4 passes, we get a mass velocity of 623. With 6 passes, we get a mass velocity of 415, which is pretty decent, And all these mass velocities, we have to see what is going to be the pressure drop now. So we do this pressure drop calculations. Very, very simple. Don't get scared by these numbers. Process engineers always have these things. They come up with this delta P log mean. And then they say, okay, 4-inch, 4 pass, the pressure drop is 620. Allowable pressure drop is only 40. So what will we do? 6 pass with 210, they are rolled out. Even 8 pass will be high. So 5-inch, okay, we get 170. 6-inch, 6 passes, we get 55. 4 pass, we get 60. 6 pass, we get 20. So we selected this 6 pass configuration, 6-inch, 6 pass configuration, because we had an allowable pressure drop of 40 psi. And I will tell you what we did with the balanced 20 psi, So I will tell you later, but that's what we selected and went ahead with. So our thinking was, okay, we have 83 million BTUs, 10,000 flux, 8,300 square foot area, 6-inch tubes, 12-inch spacing, 2D, 4,800 foot of pipe is what we have to provide, So with this configuration, we looked at the horizontal tube. We are kind of showing you that if we had to do horizontal tube heater, we will have to provide a tube removal area, which is the same space. And we, as I said, we needed space for air preheating system, fuel gas skid, ammonia injection skid. So it was impossible to put a box type heater, So we said, okay, we will select a vertical cylindrical heater for this application. So even in vertical cylindrical heater, I am showing you 3 options. So we can have 72 tubes, we can have 84 tubes, we can have 96 tubes. You can see the number of tubes are multiple of 6 and 2 because we want to have even number of tubes for each pass, and there are 6 passes, so we basically have a choice of 72, 84 and 96. When we do that, we get effective tube length of 67, 57 or 50. And we look at the tube circle diameter 23, 27, 31 and H by D of 3, 2.2 or 1.6. So anyway, if we have a tube circle diameter of 23 or 27, I think we can definitely fit it in our plot space of 80 feet by 50 feet. So we move ahead. That I will show you what we mean. So this is the first design, which is H by D of 3. So 72 tubes, 68 foot length. So we looked at it, but we did not like it. We found the burners are very close to the tubes. We don't want to give this heater. Although higher the H by D ratio, lower is the cost. A tall, narrow heater is always cheaper than a short, stubby heater, So, I mean, if I wanted to save money, we could have given this design, but we decided against this because we didn't really like it. It was violating API requirement also from that time. Now they have relaxed it. So the second option was go with 2.2 H by D ratio and number of tubes of 84. So the diameter becomes about 27 feet, the tube circle diameter. So we looked at this option. And the third option was go to 96. Now that was becoming like a very short heater. It would be good, but it is more expensive. So we decided, let's not go for this, select something in the middle and move on. So we selected the B design, but here what they are trying to show you is what is the process for sizing the radiant box. So once we know that how much tube length we have to provide and we know the number of tubes, so we get the effective tube length. And then we do this minor adjustment of the return band and we get the straight length. The straight length is about 65 feet. Then we take the return band height, clearance from arch, clearance from bottom to this one, including the expansion and creep. So we take that into account. And we come back with the total height above about 68 feet. So, and the diameter is about 24. So we have, L by D of 3. I mean, we could have sold it, actually, we could have given it, but we decided to give them a better design. So we selected option B, which was also giving us good floor heat flux of 247, API says 300. So we basically went with this type of design, actually. So as you can see, there are so many options. We have the coil size, the coil height, the number of tubes, and then we have the burner layout. And the burner layout, we want to make sure we don't go with very high heat release burner. Flame height should be less than 60% of the firebox height. And we want to make sure we have adequate burner to burner and burner to tube clearance. This is a 3D model showing our inclined firing technology, what we have for fired heaters. So this is what we had to do with. So the heater firing rate is about 138. We selected 12 burners. Each burner is about 11 feet. We calculated the burner circle diameter. So with that, we calculated the minimum required clearance as per API of 6.6. So the minimum TCD required is about 25 feet. Actual TCD is 26.7, So we kind of optimize the number of burners, the heat release, the firebox dimensions. So we do all this, several iterations, and we try to see which will give you the best and most optimum design, because we are always competing with other vendors, so we want to be cost competitive as well. So we have to make sure that we offer you the optimum, and this is what we came up with in terms of the burner layout and the tube layout. This is the outer circumference of the heater, the wall. Then we have the refractory lining, and we have this tube 84 tubes over here, and then 12 burners over here. We came up with a 12-foot burner circle diameter. The distance between burner to tube is 7 foot 5 inches. So we are very generous in terms of finding, clearances. So we give a very good, robust heater design actually for this service. Another important thing which we have to do when we are sizing the radiant section is to determine the convection section layout, because some amount of radiant heat is transferred to the bottom row or the bottom 3 rows of the convection section. So we need to determine, and here what we do is we want the convection section to be supported by the radiant section. So the way we do it is all 4 corners should fall on the radiant section casing. So we know the firebox, this thing, and we can, if we know how many tubes we are putting, we can get the length of the tubes. And we try to see whether we can get a mass velocity, flue gas mass velocity of about 0.3 to 0.4 pounds per second foot square. So that's what our objective is. So since we had a 6-pass design, we went with 6 tubes per row, and the convection section width is about 6.5. So we can calculate the length of the tubes by using Pythagoras theorem. And that's what we came up with actually. So we did it. So I think I want to stop over here and see if you have any questions, or if you have any, things we can answer it. The reason being, I mean, if you want, we can start on the Stephen-Boltzmann equation, but if you have any questions, I'll be more than happy to answer it. But okay, let's keep on going. So this is the Lobo-Evans method, which has been described by Lobo and Evans in their clarifications. And it talks about radiant heat transfer is a function of several parameters. First one is the radiation component. This is basically the Stephen-Boltzmann this thing. And then this is the convection coefficient, 7 into Tg minus Tt, So that is the convection coefficient. And then based on the fire heater geometry, we have these 3 parameters. One is the effectiveness factor, alpha. ACP is the cold plane area. And then F is the exchange factor. So exchange factor is depending on the gas emissivity. Then the partial pressure of CO2 and water vapor, and the mean beam length of firebox. So these are the 3 parameters which we will be calculating in our next webinar to calculate the exchange factor. And then we will be solving for this equation. Now, one thing I want to talk about, since we have a few minutes left, that the radiation in Lobo-Evans correlations does not depend on the flame or flame color. A lot of people talk about flames and flame color, but no radiation component is taken there. We are going by the partial pressure of CO2 and water vapor. These are the two molecules which are triatomic. And these are the ones which are responsible for radiation of uh, heat from these molecules to the tubes. So that's what is dependent on, And we will look at more, and then mean beam length. Mean beam length is the basically the length, the breadth, and the height, the three factors which we have. We use that to calculate the mean beam length of the firebox. So we will work on all these parameters in our next webinar, and we will solve for this equation and then come out with the details of the radiant section heat balance. So that's what we are solving. And if you have any question, please send it to us, and we will be more than happy to come back. So we will start with this convection section, radiant section. We will do all these calculations in detail the next time. So let me know if you have any questions. I'm more than happy to answer these questions. So I have received one question from Ganesh. Which factor affects the bulging of radiant coil? So bulging is mostly caused by high tube metal temperatures, or I should say basically from flame impingement, It may not be visible flame impingement a lot of times. It could be the hot flue gas is also licking the tubes, So high tube metal temperatures or coking or bulging is the biggest enemy of heater operators. Once you have this cycle forming up, it will be endless, and you will have to either replace the tubes in case if you have bulging, you don't have any other choice. But most of the time it is caused by high tube metal temperatures. And we have a very good technology for solving this bulging of tubes, and which is inclined firing. In inclined firing, what we are doing is we are inclining the flames away from the tubes. And when we do that, it makes a very big difference and lowers the tube metal temperatures by about 100 to 150 degree F. We have done this in two crude heaters, one at Valero, and that heater used to have shutdowns every year, almost every year or so. And after we put new burners and inclined the burners, that heater has been running for more than 5 years. So it's a very, very simple technology, and it can be done in almost every this thing. So is inclined firing compliant with API 560? Yes. I mean, there is nothing in API 560 which says you cannot do it, I mean, and we have done this in about 15 heaters. I think 6 are in India and 9 in US. And it is our default, in all our new heaters, we are putting inclined firing, and it is the way to go, So it does give us a lot of benefits, It makes sure that there is no hot flue gases touching the tubes or hot flames touching the tube, And you still get the same heat transfer. In fact, you get better heat transfer. You get a lot better heat transfer, and we can show you. You can see some of our presentations or webinars on inclined firing, and you will see it is Okay, I got a question. We say the higher adiabatic temperature, higher would be the radiant heat transfer. Yes, Siddharth. if you use air preheat, when we use air preheat, what we are doing is we are increasing the adiabatic flame temperature. And when we increase the adiabatic flame temperature, the more heat transfer takes place, I hope I'm able to answer your question. All right, guys, thank you very much. It was a pleasure doing this webinar, and keep on sending your questions. The more questions you send, I do want to tell you something. We had almost 135 people registered, and we had, I think, about 50 questions which we have received. So we will try to answer some of them in our next webinar. Thank you very much. Bye.